Okay, we are recording. Um, oh wait, I need to move this around. Get this working properly. That should be fine. Just like that. Okay, so, one moment. Okay, so what I'm going to be doing here is basically just going through these notes and also some past paper questions. Yeah, just basically just going through them for this specific topic, and then hopefully you can get onto some for um, the other topic we are doing, which is, if I remember correctly, I'll have to check. It should be transition metals, so get onto them. But we should start off with chirality and NMR. Okay, so I'm considering reading through the notes first. These are the ones on NMR. I'm presuming section 1 is chirality, so I think I'll read through chirality quickly, and then when we get about halfway, switch to NMR. So, let's check out chirality first. This is only NMR, so I will have to open up a tab for chirality as well, and move them on over like so. So yeah, these should be our chirality notes. Okay, stereoisomerism. Stereoisomers have the same structural formula but have different spatial arrangement of atoms. Okay, two types of stereoisomerism: geometrical and optical. Okay, alkenes can exhibit isomerism, stereoisomerism. Easy isomers exist due to restricted organization around the carbon-carbon bond, double bond. Single carbon-carbon covalent bonds can easily rotate. Easy isomers arise when there is a restricted rotation around the CC double bond. There are two different groups atoms attached to both ends of the restricted double bond. Okay. This is pretty simple. I think these are this is pretty easy here. Optical isomerism, move on to that. Occurs in carbon compounds with 4 different groups of atoms attached to the carbon, called an asymmetric carbon. Carbon atom that has 4 different groups attached is called a chiral carbon. Okay, got all of that down. These 4 groups are arranged tetrahedrally around the carbon. Causes 2 different isomers that are not superimposable to be formed. They are mirror images. Wonderful. Okay. Two compounds that are optical isomers of each other are called enantiomers. A mixture containing 50-50 mixture of the two isomers, enantiomers, is described as being a racemate or racemic mixture. Many naturally occurring molecules contain chiral carbon atoms, but are usually found in nature as a pure enantiomer. Okay, where were we? Optical isomers have similar physical and chemical properties, but they rotate plane polarized light in different directions. So they rotate the plane of plane polarized light in opposite directions, or different directions. One enantiomer rotates it in one direction, the other enantiomer rotates it by the same amount in the opposite direction. Okay, yeah. Different systems of nomenclature are is existent. What? Okay, I don't think that makes much sense, but whatever. R is existence for optical isomers. D/L or plus/minus are commonly used. Both have been superseded by the more useful and informative RS system. This is not on the syllabus. For information only. Negative VE in enantiomer, anticlockwise, plus VE racemate, no rotation. Okay. One optical isomer rotate light clockwise, called dextrorotatory. The other rotated anticlockwise, called lavorotatory. 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 Dextrorotatory. There we go. A racemic mixture with a racemic mixture, a mixture of equal amounts of the two optical isomers will not rotate plane polarized light. Okay, yeah, we know that. You have looked at SN1, SN2 mechanisms with haloalkanes. Yes. These reactions may involve chiral molecules as the starting haloalkane, and then the type of mechanism can determine whether the product is optically active or not. So these are very okay. It's not very long. I thought it was going to go on, but there are some more specific mechanisms that probably will be asked of us. Formation of a racemate with an SN1 mechanism. The bromine first breaks away from the haloalkane with a planar carbocation intermediate. My ghost door, sorry. Um, to form a planar carbocation intermediate, the OH minus ion can then attack from either side, resulting in different enantiomers, and a racemate forms. Because a racemate forms, there will be no optical activity in the products. Comparison with SN2 mechanism. In the SN2 mechanism, no intermediates are formed and the reaction occurs via a transition state. Okay. If the reaction was chiral, then during the reaction the opposite enantiomer would form. The product will rotate light in the opposite direction to the reactant. Makes a lot of sense. You have also met electrophilic addition route mechanisms. A racemate can also be formed in the reaction of the electrophilic addition of HBr to an unsymmetrical alkene. So I'm just looking back at the SN1 mechanism for a second. The OH is going to attack from either side, resulting in different antivirus and racemate forms. Okay, that's very understandable. So what is being formed here? Just an alcohol. So this is just, yeah, this is just producing. Okay, yeah, this is pretty simple. You've also met electrophilic addition mechanisms, race mechanisms, blah blah blah. You've read that. Okay, so if the alkene is unsymmetrical, addition of a hydrogen bromide can lead to isomeric products. The bromide can attack this planar carbon from both sides, leading to a racemate. Interesting. As well, so there's the two things that can happen. Because yeah, presumably, yeah, the unsymmetrical nature leads to it attacking from one side more than the other, and that causes the difference in the amount formed. So this should be pretty quick to get through. The chirality questions, they shouldn't be as difficult. So I'm just going to go through my thought process for every question, and hopefully I can get most of them right. I'll try and score myself out of however many it will be. There seem to be a lot of multiple choice after question 12, and then only a few longer questions. So let's get going with it. Okay, so question 1. The following molecules are structural isomers with the formula C5H10O. Which of the molecules would exhibit optical isomerism? Okay. So Immediately, I can exclude X because the only carbon, yeah, because basically a lot of the carbons are have more than one of the same species on the hydrogen, and then the only one that isn't has double bond oxygen. Um, Same with W. Um, so which of them actually has a chiral carbon? It should be, yes, it's Z. So we got the OH on the what would that be? The second carbon, I suppose. Technically. So yeah, got hydrogen, methyl, and the rest of the molecule, the R group, the OH, should be Z. So D is the answer. And then let's go to B. Which of the molecules would exhibit geometric isomerism? So just basically the one that has carbon-carbon double bond, so we're looking at Y or Z, and must be Y, I would assume. The reason I'm saying that is just because the second carbon has just two hydrogens, so you can't favor one over the other. They have to be different groups, I think, which would mean that Y is the only one that fits those criteria, so the answer would be C. Let's move on to question C. Which of the molecules would be oxidized to a carboxylic acid using acidified sodium dichromate? So oxidized to carboxylic acid using acidified sodium. I mean, potassium dichromate is what I'm used to, but it's the same principle. I'm presuming carboxylic acid, that'd be a ketone, so, and that's, it is a ketone, yeah? Or is it? No. Ketone is a secondary alcohol. Aldehyde is a primary alcohol. What am I saying? We're looking for the one that is a primary alcohol, I think. So I think we're looking for Y. So I think only Y? Oh, that's not an option. So I'm wrong. Let's look. Z only then. I mean, it can't be X. Because it's not an alcohol. It can't be X and Y because X isn't an alcohol. It can't be X, Y, and Z because X isn't an alcohol. Right? Because it has to be. Oh no. Oh no. It is an aldehyde. So that's actually X and Z. Okay, well, it can't be X and Z. So it's X and Y? Yes, X and Y, I think, would do the one. Because yeah, because then you have a primary alcohol and you have an aldehyde. They can both be. And then the ketone can't be. That makes sense. Okay, yeah. So I'm gonna go with C again. Okay, question 2. A. Which of the following compounds is not chiral? I would go B. Just because, just like right off the bat, because so many of those carbons. Oh, yeah, because even the most unique carbon in B, which is the second, like the carbon with the methyl on it, that still has two which are the same, which is the two, the two groups that form the cyclohexane. Um, they're the same because like overall the pathway is I don't know how to describe it, but the pathway is the same. So that's immediately what I'd go for. I wouldn't even consider any of the other ones. I mean, I should just look. But yeah, that D definitely is. C definitely is. A also definitely is because it's asymmetrical. So yeah, B. Okay, question 3. And when one optically active isomer of 3-chloro-3-methylhexane reacts with hydroxide ions to form 3-methylhexanol, a racemic mixture forms because. Let's reread that and make sure we got it. So, one optically active isomer of 3-chloro-3-methylhexane reacts with hydroxide ions to form 3-methyl 3-hexan-3-ol. So just a substitution. The racemic mixture forms because. So the middle two I would exclude. If we refer back to our notes, the transition state is not. Yeah, the transition state thing is not really related. So the middle two is the ones I would exclude there. So I would say it's probably the top or the bottom, a carbocation intermediate or a chiral carbon. Well, can you form a carbocation intermediate if you don't have a chiral carbon? Yes, but in the way that I mean. I'm gonna say it's A. That was my initial instinct when I read it, but I could see D. No, surely. Well, we'll learn. We'll learn, I suppose. We have a mark scheme available to us, so we can access that. Okay, question 4. Select the word that best describes the effect of a chiral molecule on the plane of polarized light. The plane of polarized light is rotated. D. That's quite an easy one. Question 5. Which of the following amino acids is optically active and produces an approximately neutral solution when dissolved in water? It's optically active and produces an approximately neutral solution. Well, if you want to think about which one's optically active, we just first have to look at which one has a chiral carbon. B immediately stands out to definitely have a chiral carbon to me. That carbon with the well, the one everyone looks at first, the one bonded to the amine group and the carboxylic acid and then hydrogen, so that one would. But the question is then, approximately neutral solution. Well, you associate approximately neutral with weaker. Oh, I see. So it's going to be the one that contains a single carboxylic acid group and a single proton acceptor. So what we're going to have is for B, I think B will be the answer because the carboxylic acid is going to lose a hydrogen and the NH2 is going to gain a hydrogen. So that's approximately neutral. A, obviously, it's not optically active because it has two hydrogens on the central carbon. C, It has two NH2 groups, which will make it more alkaline, I'm assuming. When dissolved in water. I don't know. I feel like, and then the same for D. It's just the opposite, more acidic, maybe. That's just kind of the intuitive answer there, but I don't know if it's correct, to be honest. Which of the following compounds is the isomer and contains a chiral carbon atom? Z isomer, so that's two in the same direction. So we're going to be looking at B and C, and then chiral carbon atom. B looks chiral to me, because C's got two hydrogens on that second carbon, and B only has one, and then it has three other groups, so I'm going to go with B there. Okay, which of these compounds whose formulae are shown below cannot exist as a racemic mixture? Racemic mixture, so cannot exist as a racemic mixture, so I'm just trying to visualize these because I really don't like these. Is that structural formula kind of display that they've got for the next two questions, which is great. Let's see. So if we go back to our principles, the one that cannot form a racemic mixture is the SN2 one, which would be the tertiary. No, SN2 is primary. Wait. What am I thinking here? I'm kind of associating this with the wrong thing here, clearly. So we're talking about the one that can't form a carbocation intermediate, basically. A riveting question. They're all quite similar. B has two carboxylic acid groups. So surely that one isn't even chiral whatsoever. B can't exist as a racemic mixture if it's not even chiral carbon, no? That's my concern with that one. So maybe you'd have to go B. I feel like there's something flawed with that, but that's definitely the least confident I've been on a question so far. But yeah, I'll go with that. I don't want to take loads of time on these, especially since we should be moving on to NMR and then to, if I refer back, yeah, I remember now, transition metals was the other one we're going to do. So, which of the following compounds has both optical and EZ isomers? So this is pretty simple compared to the last one. It's just two different groups on the double bond, which we have on A. We do have that on A. So A is a contender for EZ. Let's see which ones don't have EZ. All of them seem to have EZ, no? What's going on with D? D is a little strange. But it makes enough sense. B will not have easy. So we can immediately eliminate B, I think. So then optical. So out of these three, I'm guessing only one will have optical. So which one will it be? Wait, C? Does C even have easy? Yeah, it does, right? Yeah, C has easy. And C might actually be the... No, C can't be the answer because all of the carbons have either a double bond or 3 hydrogens on them. So we can eliminate C as well. So that leaves D and A. A is the same. All of the... So it has to be D. D is the only possible one, I think. And the carbon which is chiral would be the carbon bonded to the carbon which is bonded to a bromine and a CH3 group. So D is the answer. It took me a little longer than maybe it should have, but hopefully these things will speed up. Which of the following has both optical and EZ isomers? Chlorine, CH2, CH. This is the same question, but without the word compounds in there. And I think it should be similar in difficulty. Well, let's look. So A is not possible. B is not possible. So C and D are options. And C is again not possible. Yep. So it's D again. And the carbon we're looking at is the second carbon on the right hand side there. So it's the one bonded to the carbon, attached to the double bond, and attached to the chlorine and the CH3. So it's D again for 9. Is the one that drew my eye immediately. So maybe there's some intuitive speed we can pick up there. I didn't want to call it out or anything because I didn't want to do that. But okay, one alkyl reactor is also 2-chlorobutane reacts with hydroxide ions to form butan 2-ol. The organic product is a mixture of enantiomers because one optically active isomer of 2-chlorobutane reacts with hydroxide ions to form butan 2-ol. Organic product is a mixture of enantiomers because butan 2-ol contains a carbon. Okay, it's not A. It's not B. It's not C, so it's D. Again. 3 times in a row we got D. Am I right about that? Let's see. Let me just look at this again. Is a mixture of enantiomers. Wait a minute. Maybe it's C again. Maybe it's A. No. Thing is, a mixture of enantiomers, you get a mixture of enantiomers in both of the examples we looked at. So if I just go back and look at this again, you see both of these produce... Oh no, wait, no they don't. This isn't. This, I was thinking of this electrophilic addition where you get a major and a minor product with the symmetrical and unsymmetrical alkene. So actually, I think it might be C again. Same as the last one that was like this. And then another one of these, which is the formula could not rotate the plane polarized light. So just basically whichever one isn't a doesn't have a chiral carbon on it, which should be pretty easy to identify as C. We have two hydrogens on this carbon, on the second carbon, or on the first carbon, I guess. And then um, the other carbon has double bond to the oxygen. So C should be the answer there. Is the shortest one, so it does immediately draw your attention. Unless I'm missing something, but I don't think I am. Yeah, okay. 12. Getting on to the longer questions, and then we'll be on to the NMR, which is a little bit more difficult, maybe. Okay. 12. 2-hydroxypropanoic acid, lactic acid, is a chiral molecule which is found in mussels and in sour milk. Explain the term chiral, stating the feature of 2-hydroxypropanoic acid that makes it chiral. Okay, so from what I know, a chiral carbon is a carbon, and I'm just writing this down so you can just hear me saying it, but I'm writing it down for myself. Is a carbon that contains 4 unique groups attached to it. That is attached. That is attached to 4 unique groups. Okay, that is going to be 1 mark. Now let's identify where the other 2 come from. Okay, so now I have to state the feature of the 2 hydrogens that makes it chiral. That's another one, and then labeling it on the formula above is the 3rd mark. So, stating the feature of 2. The second carbon, if I'm not mistaken. The second carbon on 2-hydroxypropanoic acid makes it chiral. Well, we're officially over half an hour in, which is lovely. Only 3.5 hours to go. Shouldn't take that long to get through all of this. But if I do get through it fast, I might upload another one later on biology. But right now, basically, I have giving myself 2 hours to get this done, or a bit less, about an hour and a half to get this all done. All the chemistry stuff done, and then I'll see what I can go on to in the afternoon. But working quite efficiently so far, almost through chirality. And then once NMR is done, we've been taking half an hour to get through chirality. NMR maybe take 40 minutes. Pretty hopeful. Okay, let's carry on with the question. So what I was writing was the second carbon on 2-hydroxypropanoic acid was the one that makes it chiral. Because it's attached to 4 unique groups. And then I believe we have to label it with a asterisk. Asterisk? And then asterisk. Something like that. Which will be this carbon here. So I'm just going to write label second carbon asterisk because I'm not going to draw the whole thing out. And let's move on to AII, which is only 2 marks, so give me hope. My dread would be that there is a 5. Oh dear. Okay, this is NMR. We can ignore this. Look, no, not a single 4 marker in the whole of chirality. 3 markers the highest. First question in the NMR is 4 marker. Gotta love it. And then a 7 marker, and then a 6 marker. Oh yes, but it's, I believe, accurate too. I could actually, there should be another whole set of questions on these, so I will go over them, those questions, probably next week. Then I'll move on to past papers, I think will be the way to go. But okay, let's finish off this. 2 marker. What is the difference between the 2-hydroxypropanoic acid formed in mussels and that found in sour milk, which gives rise to the difference in optical activity? Wow. That's a great question. So we can see here above, which I didn't actually read out, it says the 2-hydroxypropanoic acid formed in mussels, but the sour milk is not. So that means this one forms different enantiomers, and this one forms a racemic mixture, the sour milk one. What makes it form a racemic mixture? That is a wonderful question. And the thing that makes it form a racemic mixture is that it takes place in an SN1 mechanism where a carbocation intermediate is formed. But why? What determines the type of mechanism? Nobody knows. I think we might not need that for the answer. We might though, which would drop us some marks here. Let's hope not. Let's hope not. Okay. These questions a little bit more annoying to answer. I'm going to say the 2-hydroxypropanoic acid formed in mussels is formed from a carbocation intermediate in an SN1 mechanism. Oh no, other way around. The 2-hydroxypropanoic acid formed in sour milk is formed from a carbocation intermediate in an SN1 mechanism which forms a racemate which is not optically active. So what I'm hoping here is that it doesn't want me to explain why a racemate is not optically active. So why the fact that there's a 50-50 ratio in there. I could include that in an exam. Probably I would. I'm not going to waste time writing out a whole paragraph for 2 marker. This is the whole point of this, to get experience and know what the questions are looking for. So hopefully they're not looking for that, and I guess we will find out soon. But yeah, that's just my final verdict on that, and then we can move on to 12B or whatever this is. 12B, yes. Okay. 2-hydroxypropanoic acid may be prepared in the laboratory from propanoic acid, a 2-stage sequence by which 2-bromo-propanoic acid is formed as an intermediate. carbocation intermediate or not? Well, if we look at it, there is definitely not a carbocation intermediate because there is no ion, but there is an intermediate, which is the 2-bromopropanoic acid. So this is reminiscent of something we have seen. It's just a two-stage mechanism. There's no little nuance thing in this. I think it's just that. So stage 2 of the sequence was carried out in 2 steps. Identify the reagent required for each step in stage 2. Well, if it's carried out in 2 steps, that was assuming it's SNO1. 2 steps. This is like 1 step but with the transition state. So reagent required for stage 2 is just the 2-bromopropanoic acid. So we can just go with that. Now, I'm not sure if it wants, because this is a red phosphorus. So I have been made aware of that. So I don't know if there's something else going on here that I'm completely missing. It's possible. We'll find out. And then I need to refer to that, and then the reagent required for each step is stage 2. Second step should just be OH minus. So the reagent wouldn't be OH minus, the reagent would be something like KOH, I imagine. I'm going to put KOH and leave it at that because I think that's all I am understanding from that. And then 12 BII. When an optically active isomer of 2-bromopropanoic acid is used in stage 2, the resulting 2-hydroxypropanoic acid is also optically active. State and explain what this indicates about the mechanism of the first reaction in stage 2. So we have this here. This, oh, sorry, this. This is that. This is what that is, the SN2 mechanism. So the first thing for 1 mark will be it's SN2, indicates it's SN2. Where do the other 2 marks come from? That is my question. So let's try and figure this out. Where are the other 2 marks? State and explain. So I guess it's just the explanation of why it's optically active, not of why it's SN2. So, it is optically active because the produced isomer is SN2. That's not what I'm thinking. The produced isomer is optically active because the mechanism is SN2. So now I have to say in an SN2 mechanism, a transition state occurs or it is, I don't know, there is a transition state occurs. No, this is not what I need to say. I didn't talk about the transition state yet. I need to say the the OH minus ion can only attack from one side uh, of the carbon atom because the other side is already bonded to the bromine. That means that only one type, or only one enantiomer can be produced. That's what I need to say. Um, the OH minus ion can only attack, I don't know if attack is a word that would be allowed, but I'm going to try use it. Can only attack the central carbon, the chiral carbon, from one side due to the bromine carbon bond this means that only one enantiomer this means that only one enantiomer can form from the carbocation, from the mechanism, from the reaction, form in the reaction. This means that the product will be optically active. Because do I need to explain that? I might need to explain that. I'm not going to do it now, but we hope we don't have to. We've written quite a lot for 3 marks, or about at least enough, I would expect. So maybe I've waffled, and that's why I've written quite a lot. But I don't know. Maybe that extra bit of explanation is required. But now is the time to look at the mark scheme because we've now finished this section. So that's what I'm going to do. I'm going to go and pull up the mark scheme. Quickly. Here we go. Apologies. This should be the mark scheme. Yes, and let's pull that up here and take a look. So, question 1 we had as D. Perfect. Question B we had a C. Correct. Question C we had a C. So we don't need to review these because I got them right. I understood it. The reinforcement happened during the question. I don't need to question what I'd done and what I'd been reinforcing to myself. So I'm just going to take these and say that we had the proper understanding. B is correct. A is also what we had. D is what we had. So maybe we'll go full marks on this. B was what we had. B is again what we had. B is again correct. D and D again, correct. And then C and C again. Okay. 11 out of 11 on the multiple choice. That is what we want to see. Now, let's go into these because I'm not so hopeful. So, Kernel molecule is a non-superimposable on its mirror image with no planar symmetry. 4 different groups attached. So we completely missed the chiral molecule. Thing. We missed that. So a chiral molecule is a non-superimposable on its mirror image. So let's just annotate that. Molecule is non-superimposable on its mirror image. So what I understand that to mean is basically you take its mirror image, so it but flipped, and you can't lay them over each other and they'd be identical. You'll see something different if you overlaid one over the other. Um, okay, so we got 1 mark for the saying the second carbon on hydroxypropanol acid makes it chiral because it's attached to 4 unique groups. That's what I have. So that's 1 mark there. Mark point 2, and then yeah, asterisk on the second carbon is correct there. So that's 1.3. So 2 out of 3 there. Keep that in mind. So I clearly misunderstood the definition of a chiral carbon. So if I scroll up and find the definition of chiral carbon, probably just kind of ignored it because, okay, called an asymmetric carbon. A carbon that has 4 different groups attached is called a chiral carbon atom, but not a chiral molecule. Assuming that's the differentiation I had to make. What's the question? Explain the term chiral, not chiral molecule or chiral carbon, just chiral. Maybe, oh, but the feature of 2-hydroxypropanoic acid that makes it chiral, so referring to the whole molecule there is chiral. Okay, I kind of, and then it says chiral molecule up here as well. So that's clearly the association that I needed to make there. Kind of missed that, but you know, it could be worse. AII, hydroxypropanoic acid formed in muscles, is a single enantiomer, unequal mixture. Did not mention that. So what was the question here? What is the difference formed in muscles and salmon that gives rise? So I actually have to mention both. Racemic mixture of 2 enantiomers. So I just focused on why hydroxypropanoic acid was not optically active. But actually you have to mention both. That's very simple. That's something I've done many times before. So 1 out of 2 there. Quite easy to fix, but also something that missed quite a lot, I guess. And then 12B, KOH is the first step, and the second step is HCl. Wow. So stage 2 is what am I looking at here? Stage 2 this here, or I mean I'm trying to highlight these, it's not working, but so yeah, it's SN2 then. I don't really. Let's just look at this like this. It's easier. Well, I think it's the same here. Yeah, I can still see it. Okay. Um. So we're just going. This is the same reaction, both ways. So what I thought I was looking at was it's SN1, and this is the first step with the breaking of the bond, and then this is the second step, and that's where you have to say the, for example, KOH. However, I do not think that was what it was looking for. So what is this? The hydrochloric acid thing. Formation, it's just nucleophilic substitution, no?
So if it's just nucleophilic substitution, I think I just didn't associate this with like the normal reaction, like the normal just haloalkane to, because this is a catalyst, yeah, acid catalyst. So yeah, 0 marks for that one. Um, Fairly easy, but I think this isn't like exclusively like you don't need to associate this with the chirality topic to get it right. That's the thing, yeah. And then the second one, hopefully we can score some more marks. When an optically active isomer of 2-bromopropanoic acid is used in stage 2, the resulting, yeah, I've read this, so that's just the question. And first mark, or assuming mixture is not formed. Okay, direction is SN2, so that's 1 mark there. I can see mark point 2. Third mark, only attacks from one side of the molecule from the opposite side to the leaving group. So I've written the produced isomer is optically active because the mechanism is SN2. In SN2 mechanism, the OH minus ion can only attack the chiral carbon from one side. So I have written that, so I'm going to give that the third mark there. But I'm looking for the first mark here. Due to the bromine carbon bond, blah blah blah. This means that that only one enantiomer can form in the reaction. Is that the first mark? More of one enantiomer is formed. Only one enantiomer is formed. I would say that is the third mark there. So actually, I'm pretty sure that is a full marks, 3 out of 3 on that. So that's good. Bit of a redemption. Okay, we're 57 minutes in, so we are an hour in. But I believe if I switch to my sheet here, and I think I can switch to it on. Okay. But how do I switch? Don't I move this out the way? I can. However, it's not correctly sized, so let me just do that. Okay, this is just a bit off. I just make it normal size and then just exclude. That's good enough, I suppose. Okay, so we can now score ourselves. So that's definitely an hour. So definitely 60 minutes. We can give ourselves the 60 minutes green there. So good streak, and we just test ourselves. So let's score. So 11 out of 11, 2 out of 3. So that puts us to 13 out of 14. And then we got 1 out of 2 on AII, so that puts us to 14 out of 15, 14 out of 16, sorry, 14 out of 16, and then 14 out of 18 because we missed the 12B I, and then we go from 14 out of 18 to 17 out of 21. The full marks on the last question. So I can score myself there, which is as a percentage. I should do that for this one actually. So I believe my percentage was 84. this. So I'm going to score 84 there. And then let's just quickly calculate what that's going to be. So 17 out of 21 is 81%. So pretty happy with that. So yeah, with this one up here, I had it as the percentage before. Oh, 48 and the percentage is 84. Wait, is that correct? Sorry, just one moment. Yeah, 48 out of 57 is indeed 84. So that was correct. So full green, at first full green. So good start considering this is the first set for the videos. Obviously this is like we almost had it here, but we should have full green here because if you can see, basically did not do a whole lot on my organics. Not because I don't like organics. I do definitely like organics. I just didn't really give myself time. Basically, I had spent about 2 hours total. This basically, I put 60 minutes here. Doesn't mean I did 60 minutes only. I basically might have spent an hour and a half on this, but very slowly, very inefficient. So really, I was taking up, an hour and a half, 2 hours of my time revising, but I was only doing 60 minutes of solid work. So that's why I put this, but we have basically been working solidly for 60 minutes, so I'm quite confident to say this is 60 minutes. Transition metals now. I will probably make that a separate video because an hour, 2 hour long video, whatever it's probably going to be, will be pretty hard to upload to YouTube. So that is the logic there behind that. Okay. I'm gonna end it there, and I guess I will be. What is this? Oh, that's just my other one. Okay. I guess I will be back soon, and we'll finish off on that. Let's just get this back to where it was, just like that. Yeah, we'll be back on that soon. And yeah.